so let's say we have this system of equations, 4 equations with 5 unknown variables, a, b, c, d, and e. So a plus 2b plus 3c plus 4d plus 5e equals 0. 2a plus 4b minus 3c minus d plus 10e equals 0. 3a plus 6b plus c plus 4d plus 10e equals 0. And 4a plus 8b plus 5c plus 9d plus 20e equals 0. This is essentially the equivalent of, well, if we had something like, let's say, 3x plus 4y plus 5z equals 0. That's something we might actually be able to visualize in 3 dimensions. If you were to graph this in 3 dimensions, what sort of region or what sort of shape would you get? Or what if we scaled it back 1 more dimension? Let's say you were just graphing like 5x plus 8y equals 0. This is going to be a line, right? Because you could solve for y and get y equals negative 5/8 x. So that'll be a line, and that is in particular a line that passes through what point?
The origin?
Yeah, this is going to be a line that passes through the origin. If we add in 1 more variable, we're scaling it up to a 3-dimensional universe. And what shape would this form? It's not just going to be a line. Yeah, it's going to be a plane. So this would be a plane that also passes through the origin because 0, 0, 0 is going to make this equation true. So this would be a line through the origin. This would be a plane through the origin in a 3-dimensional universe. In this case, we've got a similar idea. We've got a linear combination of 5 variables adding up to 0. It's now in a 5-dimensional universe. So instead of being a 1-dimensional line in a 2-dimensional universe, or a 2-dimensional plane in a 3-dimensional universe, these are going to be 4-dimensional spaces in a 5-dimensional universe. So basically like a plane, but scaled up a couple more dimensions. However, they are still all going to pass through the origin because 0, 0, 0, 0, 0 makes every one of these equations true. So these are all going to be shapes that meet at the origin. By solving this system of equations, we're trying to figure out, are there any other points where they meet? In the same sense that, for instance, if you got 2 planes that pass through the origin, they're going to meet at the origin, but there could also be an entire region of other points where they meet. So that's what we're trying to figure out here. Geometrically, we're trying to figure out, do these hyperplanes have any other locations where they meet other than just the origin? So that's one way to interpret what's going on here. Another way to interpret what's going on here is that we could also think of this as vectors. If you look at all the coefficients of A is being multiplied by 1, 2, 3, and 4. So we could think of this as A times the entire 4x1 vector, 1, 2, 3, 4, plus B multiplied by the vector 2, 4, 6, 8, plus C multiplied by the vector 3, negative 3, 1, 5, plus D multiplied by the vector 4, negative 1, 4, 9, plus E multiplied by the vector 5, 10, 10, 20. And all those would have to add up to the vector 0, 0, 0, 0. So this system of 4 equations, 5 unknowns could also be thought of as one equation with 4 or 5 unknown vectors being added together with some unknown, or 5 known vectors with unknown multipliers. And we want to know, is there any combination of coefficients A, B, C, D, and E that will make these add up to the 0 vector? And there's one solution we can guarantee already. What values of A, B, C, D, and E are guaranteed to make these vectors add up to the 0 vector? Yeah, if these are all 0, then this is guaranteed to work. 0 times this vector plus 0 times this vector and so on. If all the coefficients are 0, then this is guaranteed to work. So we know that one solution is for all of these vectors to equal 0, or all these coefficients, I should say, for all of these variables equals 0. That's guaranteed to make this equation true. But the big question is, are there any other solutions? Is 0, 0, 0, 0, 0 the only solution, or do we have more solutions as well? Because it's entirely possible for a system of linear equations to have multiple solutions. So let's try that out. One way to solve this, we could solve this using techniques from, let's say, high school algebra. It's possible to solve this using the usual methods of substitution and elimination. For example, we could solve for A. We could say A equals negative 2B minus 3C minus 4D minus 5E. Substitute that in the other equations and reduce the number of variables. And then solve one of the other equations for another variable and plug that into the other equation and so on. But that gets really tedious with so many variables. You could also use elimination. For instance, if you wanted to combine the first two equations in a way that gets rid of A, how could you combine those to get rid of A entirely?
Multiply by -2.
Yeah, if you multiply the entire top equation, both sides by -2, it's going to become -2A minus 4B minus 6C minus 8D minus 10E. And then the other side, 0 times -2 is still 0. If we then take the second equation exactly as is, and add those together, the A's cancel out, which is what we want. And it so happens that the B's also cancel out. -6C minus 3C is -9C. -8D minus D is -9D. And the E's also happen to cancel out by coincidence. We could then also divide both sides by -9 and just get C plus D equals 0. So that is a much simpler equation that we got from the same information, but this now tells us something much more useful about how C and D are related. Specifically, that C has to be the opposite of D. Any questions on that so far? And then we could also try combining other equations in other ways, maybe adding -5 times this equation to this equation to get the C's to cancel out, for instance. Or we could also substitute -D every time we see C to further reduce the number of variables. Ideally, we want to reduce this to as few variables as possible so we can get information about what the variables have to equal. Any questions on those techniques so far? There is, however, a much more streamlined way to do this. Since we have all of these equations written in the same format, since they're all something A plus something B plus something C plus something D plus something E equals 0, then we don't really need to list out the variables. Like this equation, 4A plus 8B plus 5C plus 9D plus 20E equals 0. We could just list that as the numbers. We could just list it as 4, 8, 5, 9, 20, 0, with the assumption that the variables don't need to be listed. We can just say, we already know that these are going to be multiplied by A, B, C, D, and E and added up. So let's just write this as a list of numbers. First equation, just looking at the coefficients, 1, 2, 3, 4, 5. Second equation, 2, 4, -3, -1, 10. Third equation, 3, 6, 1, 4, 10. And fourth equation, 4, 8, 5, 9, 20. And then we've also got an equals 0. So I'm just going to list 0, 0, 0, 0. And we often put a bar here to represent the equal sign, or to separate it into the coefficients of the variables and the numbers on the other side of the equation, which in this case happen to be all zeros, but they don't necessarily have to be. And we usually draw that in brackets to group it all together. And this is usually called an augmented matrix. A matrix just means a rectangular grid of numbers, a convenient way of organizing information. And when we say augmented, Augmented just means enhanced with something else added to it. So we've got the matrix of coefficients, all the coefficients of the variables A, B, C, D, and E, and it has been augmented with one extra column. So the augmentation just means an extra column or possibly several extra columns attached to the end. And this really does represent the exact same information as the system of equations. We're just leaving off the variables. Instead of writing the variables as symbols, we're essentially representing it as place value. For instance, this 3 is interpreted as a coefficient of C, the third variable, because it's in the third column. So this entire first column, 1, 2, 3, 4, those are the coefficients of A. The entire fourth column, 4, -1, 4, 9, those are the coefficients of D. If there was a variable that was missing from an equation, like let's say this equation didn't have D at all, we would just put a 0 there as a placeholder. So this is all the same information as the system of equations. We're just writing it as a more streamlined format. Any questions on that representation so far? And you could also think of this as representing the vector equation we were looking at earlier, the idea of A times the column 1, 2, 3, 4, plus B times the column 2, 4, 6, 8, and so on, equals 0, 0, 0, 0. That's just A times this column as a vector, plus B times the second column as a vector, plus C times the third column as a vector, and so on, equals this final column of all zeros. So the same information, whether it's written as a system of equations or as one vector equation, both of those problems can be written as the same augmented matrix. So the same augmented matrix can represent these two different kinds of problems. The textbook usually calls this, the equation system, the row picture of the matrix, in the sense that we're interpreting each row as an equation, and then calls this idea of vectors added together the column picture of the matrix, in the sense that it's the same matrix, but we're treating each column as a vector, and we're looking at what linear combination of those vectors will add up to 0 or whatever we're looking for. So same information, same matrix representation, even though that can represent these two seemingly different problems. Any questions on that augmented matrix so far? And then to solve this, we're going to be doing this process called row reduction. Excuse me. And the row reduction process using row operations is essentially equivalent to this idea we were doing up here, with multiplying an equation by some scalar, some real number multiplier, and adding it to another row, another equation, to get some of the variables to cancel out. So same idea of elimination, adding a multiple of some equation to another equation. The only thing different is we're going to be representing it as rows of the matrix instead of equations in a system of equations. Same information, just written in a different way. So we're going to do that by, let's start with the same thing. I notice we've got a 1 here. We could use that 1, and remember that's really 1a, we're just not writing the variable. We could use that 1a to cancel out the 2a using this same idea. We're just going to look at it in terms of rows. And we're going to think of this as modifying row 2, keeping row 1 the same, but modifying row 2 by adding -2 times the first row. So we're keeping row 1 exactly the same, but we're modifying row 2 by adding -2 times the first row. So let's see what that's going to look like. First row, we're keeping exactly the same, so I'm just going to copy that down exactly as is. But the second row, we're modifying by adding -2 times the first row. So we're going to take something from the first row, 1. We're going to multiply it by -2, so we get -2. We're going to add it to whatever's in the second row, 2. So 2 plus -2 times 1 cancels out to 0, which is exactly what we want. The whole point of this is to use this number here to turn the number below it into a 0. And that number we usually call the pivot. Formally, the pivot is the first non-zero number you encounter in the row. The first non-zero in the row, as you read from left to right. So you take the first row, identify the first non-zero in it. That's your pivot. You're going to use that to eliminate the next number down. So we're using this top row, multiplying by -2, and adding it to the second row to eliminate the number under the pivot. And then we got to carry through that operation for the rest of the row also. The 4 that's already there, we're going to add -2 times the 2 in the top row, which means we're adding -4. That also happens to cancel out. That's not always going to happen. In fact, that's not usually going to happen. The important thing is to get the number below the pivot to cancel out. It may be the case that some other numbers happen to cancel out also. Next, we've got -3. We're going to add -2 times 3. So we're adding -6 to the -3 that's already there to get -9. Then we've got a -1. We're going to add -2 times 4. So that's -8 added to the -1 that's already there. That's also -9. And then 10, we're going to add -2 times 5. So that's -10 added to the 10 that's already there, cancels it out. And then 0 plus -2 times 0 is still 0. So this is our new second row. It overwrites the original second row by modifying it. Any questions on that so far? And then formally, since we didn't change row 3 and 4, we copy those down directly and then proceed from there. But we can actually save some time and space by combining several steps into one. For example, if we take a look at the third row, we've got a 3 here that we'd like to cancel out, still using the same tool, still using the pivot from earlier. How could you use this 1 to cancel out this 3? What multiplier would we have to use there?
-3.
Yeah, so we're going to modify row 3 by adding a multiple of row 1, specifically -3 times row 1. By the way, this isn't the only way to do it. There are other ways to get this 3 to cancel out. For instance, you could use, let's say, 3/4 times the fourth row added to the second row or the third row to cancel out the 3. But in order to keep things as streamlined as possible, to make it as algorithmic as you can, take all the decision making out of it and just have the same procedure every time, it's very useful to start from the top row, identify the pivot, use that to eliminate everything under it, the 2, the 3, and the 4 in this case, so that you're doing the same procedure every time. This makes it a lot easier to figure out what to do next. It takes all the guesswork out of it. And it also means that since it's the same step-by-step procedure each time, it becomes much easier to write a computer program to do it for you. So let's try this operation. We're adding -3 times row 1 to overwrite row 3. So we've got the 3, we're adding -3 times 1 added to the 3 that's already there. And what do we get?
Zero.
Yeah, that's the 0 that we wanted to create in the first place. And then carrying the operation through to the rest, we've got a 6. We're adding -3 times 2, and what do we get? Also happens to be 0. And then 1 plus -3 times 3, what do we get there?
-8.
Right, because we're adding -9 to the one that's already there, so we get -8. And then 4 plus -3 times 4 is going to be, right, -8 again. 4 plus -12 is -8. And then 10 plus -3 times 5. Right, that'll give us -5. The 10 plus -15. And then 0 plus -3 times 0 is still going to be 0. In fact, if this final column is all zeros, it's just going to stay 0 the whole time anyway. So in fact, we don't even really need to write this column of all zeros. If it really is a column of all zeros, we could just leave that out and fill it in at the end, because it's not going to change. If it was anything other than all zeros, we would need to very, very carefully keep track of it though. And let's go ahead and finish off the fourth row also. What operation could we do to the fourth row that would cancel out the number under the pivot?
-4 times row 1.
Yeah, we can add -4 times row 1. And let's see what we get there. What's that going to turn into? What numbers should we get there? If we're taking everything from row 1, multiplying by -4, and overlaying that on top of the fourth row. Yeah, I think that should work. We got 4 minus 4, 8 minus 8, 5 minus 12, 9 minus 16, 20 minus 20. That should work. And by the way, if you're having trouble seeing where the numbers are going, what's often useful is to write out that -4 times row 1 or whatever as a separate row. If you just separately take row 1, multiply everything in it by -4, you get -4, -8, -12, -16, -20, 0. And then we're adding that to the fourth row. 4, 8, 5, 9, 20. So if you're having trouble keeping track of the numbers, it can often be useful to write out those rows separately off to the side. -4 times the first row plus the fourth row exactly as is, -4 plus 4, -8 plus 8, -12 plus 5, and so on. And that's your new fourth row. Any questions on those row operations so far? So in general, when you're doing these row operations, when you are row reducing an augmented matrix, you're always allowed to add a multiple of a row to another row, because that's just equivalent to adding a multiple of an equation to another equation. You're allowed to do that in a system of equations. It doesn't change the information, it just changes how it's being written. Also, another thing you can do, without any addition at all, you can just multiply both sides of an equation by some scalar. You can do the same thing for a row, just multiplying everything in a row by some scalar. This is never, strictly speaking, necessary when you're doing row reduction, but it's often very useful. Because, for instance, what do you notice about all the numbers in row 2? Is there any multiplier or divisor that's going to make those numbers easier to work with? Yeah, if we divide everything in this row by -9, and this corresponds to the what we were doing with the equations earlier. When we added these, we got -9c minus 9d equals 0. And then we proceeded by dividing both sides by -9 to get just c plus d equals 0. We can do an equivalent operation dealing with the rows. We can take this entire row and multiply it by -1/9. That is multiplying every number in this row by -1/9. That's equivalent to multiplying both sides of an equation by -1/9. So this is another thing you're always allowed to do in an augmented matrix. You can always multiply or divide some row, everything in the row, by some scalar, except 0. You can't multiply it by 0 because that would lose all the information. You want to keep some information, just modify how it's presented. The third row, 8, 8, and 5 don't really have any nice, neat common factors, so I would just leave that alone. Maybe multiply by -1 to make it all positive. Not really necessary, but it'll make it a little easier to write. And then the fourth row, since everything in there is either 0 or -7, let's multiply that whole thing by -1/7. and see what we can do with that. So let's see what we get. Some more space. So first row, we're keeping the same. 1, 2, 3, 4, 5. Second row, we're multiplying by -1/9. So we get 0, 0, 1, 1, 0. Third row, we're just multiplying by -1. So we get 8, 8, 5. Fourth row, we multiply by -1/7, and we get 0, 0, 1, 1, 0. And in this case, I'm going to leave off the column of all zeros because we know that's not going to change anyway. Again, if it's not all zeros, make sure you include it and keep very close track of it because the changes will be very important. But if it's a column of all zeros, we know it's never going to change anyway. We can just leave it off and fill it in again at the end. So, investigating the pivots. The first row has this 1 as a pivot. And the important thing about that 1 is that that 1 is now alone in its column. That's very useful because if we translate this back into a system of equations, this 1 was a coefficient of what variable? Right, that was a coefficient of A. The fact that there's only a single value in this entire A column means that A is only going to show up in one equation. That's tremendously useful. It's going to make it a lot easier to solve for A if A only shows up in one equation. So that's what we want to do with the pivots. Anytime you've got a pivot, you want to use that pivot to get rid of everything else in the entire column so that that variable only shows up in one equation. Also, it's very convenient if each pivot is the number 1 because then you just have one A plus a bunch of other stuff. So those are the main things you want to go for. Your goals here, every pivot should be alone in its column. Every pivot should be the number 1, although that's easy to do as the last step. Like if your pivot is 5, you just multiply that row by 1/5. And also just for convenience, you want the pivots to be in order from top left to bottom right so that you can read it off more easily. Let's take a look at the second row. What's our next pivot? Does the second row have a pivot? The second row? What's our first non-zero number we encounter there? Not from the original matrix, but from the new version of it. Yeah, if you take the second row and start reading across from left to right, the first non-zero you encounter is this 1 here. So that's going to be our new pivot, our pivot in the second row. And it's already a 1, which is convenient. If it wasn't a 1, we could still use it with whatever number it is and then turn it into a 1 later. But we want to use this pivot to eliminate everything else in the same column, both above and below. So for instance, how would we modify the first row using the second row to cancel out that 3? What could we add to the first row? One-third? If you multiply the second row by 1/3, would that cancel out the 3? So what should we multiply? Because remember, we're not multiplying row 1 by something. We're multiplying row 2 by something and adding it to row 1. So what multiplier attached to the 1 would allow it to cancel out the 3? Yeah, 3. And also, since we want to add to cancel it out, we should include a negative as well. So we're going to modify row 1 by adding -3 times row 2. We're not actually changing row 2. We're keeping row 2 the same, but we're using multiples of row 2 to modify the other rows. So let's see what the new row 1 looks like. 1 minus 3 times 0, still 1. 2 minus 3 times 0, still 2. Note that the zeros we already have means we're not changing those values in the other rows. And then 3 minus 3 times 1 cancels out. That's what we wanted. 4 minus 3 times 1 becomes 1. 5 minus 3 times 0 becomes 0. Or no, still 5. We're not changing it. Second row, we're keeping exactly the same. 0, 0, 1, 1, 0. And then what about the third row? How can we modify the third row to use this 1 to cancel out the 8? What would we need to add to the third row? Yeah, we'd add -8 times row 2. So 0 plus nothing, 0 plus nothing. So we get to keep the zeros we've already established. This is one of the big advantages of working in order from top left towards bottom right, that you establish some zeros and then you keep them. You don't have to mess them up. 8 plus -8 times 1, 0. 8 plus another -8 times 1, also 0. And then 5 plus nothing is 5. So we've gotten a lot more reduction here. We've gotten more zeros. The more zeros you can establish, the simpler the remaining equations are going to be. And then for row 4, we want to use this 1 to cancel out this 1. So what should we add to the fourth row? Yeah, just -1 times R2, or you could even just write that as -R2. In fact, you could even think of it as just subtracting row 2 from row 4. And what does that turn into? What happens to the fourth row when we subtract the second row? Yeah, it's all 0. The fact that we've got a repeated row here, the fourth row is identical to the second row, means the fourth row is going to cancel out completely. And note that that wasn't really obvious from the original system of equations, but it emerges from the row reduction. And that's very useful because it means that this fourth row doesn't really provide any information. If we were to rewrite that as an equation again, you'd have 0a plus 0b plus 0c plus 0d plus 0e equals 0. In other words, 0 equals 0. If you've got a row of all zeros, that just tells you 0 equals 0, and we already know that 0 equals 0. So this row does not provide any real new information. Instead, essentially, we can ignore that row and treat this as a system of 3 equations, 5 unknowns, instead of 4 equations, 5 unknowns, since it turned out the fourth row didn't really provide any information. Any questions on that so far? So now that we've established that, we've got our first pivot is now a 1 and alone in its column. Our next pivot is a 1 and alone in its column. What's our next pivot?
Five.
Yeah, in the next row, the first non-zero we encounter is 5. So we want to, once again, we want to use that pivot to eliminate everything else in that entire column. And eventually we want to turn that pivot into a 1 instead of a 5, but we can do that later on. I think it might be best to leave it as a 5 here because we want to use this 5 to cancel out what else? What do we still need to eliminate here?
The 5 in the top?
Yeah, we want to eliminate the 5 that's above it. We want to eliminate everything else in the same column, which is just that single 5. We can do that by adding what here?
Negative row 3.
Yeah, if we just add negative row 3, the 5 will cancel out the 5, and these zeros don't do anything because we're just adding a bunch of zeros. So filling that out anyway, just to get one last step, we're modifying row 1 by adding a bunch of zeros, so the first 4 numbers don't change. And then 5 gets a -5 added to it, so that cancels it out. Second row, no change is needed because there's already a 0 there. Third row, ideally, what number do we want that pivot to be? Yeah, we want that to be a 1. So in this same step, let's go ahead and multiply that row by 1/5. That way, all these zeros stay 0, but the 5 turns into a 1. And then the fourth row is still all zeros. We don't really need to include that because a bunch of zeros doesn't really provide any information, but it's a good idea to include it anyway, just to keep it the same size of matrix. And since we're now done, I'm going to go ahead and add in that row of zeros that has been invisible, or the column of zeros that was invisible the whole time. Now, an important thing to check here, going back to the idea of the pivots. Our first pivot is a 1, and it's alone in its column. Everything else in that column is zeros. Our next pivot, first non-zero we encounter, is a 1, and it's alone in its column. The next pivot is also now a 1, and now alone in its column. And the fourth row doesn't have a pivot at all because it's all zeros. So this matrix, once it's had these row operations done to it, it now has only 3 pivots. And we now have each pivot is a 1, each pivot is alone in its column. All the pivots are in order from top left towards bottom right. And also the fourth requirement is that if there's any rows of all zeros, which there are, they have to be at the bottom. Once those 4 requirements are fulfilled, we call this reduced row echelon format. Or RREF. And again, those 4 requirements are every pivot is a 1, every pivot is alone in its column, everything above and below is 0. The pivots are all in order from top left towards bottom right. It's possible to skip columns, but they've got to be in order from top left to bottom right. And if there are any rows of all zeros, that is any rows that don't have pivots, they have to be grouped together at the bottom. As long as you meet those 4 requirements, this counts as reduced row echelon format, or RREF, which is basically the most simplified you can possibly make this system of equations. Any questions on the terminology there so far? And now that we've got it to reduced row echelon format, we can actually use this information to solve the original system of equations really quickly. The process of going through the row reduction can be kind of tedious, but ultimately in most real life cases, that would all be done on a computer anyway. The important thing is knowing how to do it and knowing how to interpret the results. What we can now do, I'm going to clear out some of this first few steps. What we can now do is rewrite the few rows we have left as equations again. Going back to, for instance, the first row, 1, 2, 0, 1, 0, 0. If you rewrote that row as an equation using the original variables, what would that equation look like?
A plus 2B plus 4, no, plus D, no 4.
Exactly. We've got 1A plus 2B plus 1D, no C or E at all, equals 0. And what about the second equation?
C plus D equals 0.
Right. C plus D must equal 0. And note that that's the piece of information we found from working with the equations on their own in the first place. This is just an alternate way of getting the same information. And then the third row as an equation. Yeah, this leaves out A, B, C, and D. We just have 1E equals 0. And what about the fourth row? If you wrote that as an equation. Yeah, that's just 0 equals 0. More formally, you might say 0A plus 0B plus 0C plus 0D plus 0E equals 0. But that's just 0 equals 0. And 0 equals 0 is always true, no matter what the values of the variables are. So this doesn't really provide us any new information. A row of all zeros is basically just saying that row doesn't care what the variables are. It doesn't provide any restrictions. The other rows do provide restrictions. Like the third row says E has to be 0. The second row says C and D have to add up to 0. The first row tells us how A, B, and D are related to each other. So this at least gives us some information about how the variables have to be related. And a very useful way of portraying that information is to solve for the pivot variables. I mentioned earlier, the whole reason we're getting the pivots alone in the column in the first place is so that that variable only shows up in one equation. This column is empty except for this single number 1, which means that 1A shows up only in that one equation. making it easy to solve for A. In fact, if you isolate A, what do you get?
-2b minus d.
Right. So we've solved for the pivot variable in terms of variables that do not have pivots in their column. We call those free variables. B and D here would be the free variables, free in the sense that they are free to be any values. You could choose any value you want for B and D because there's no restrictions on them. And that tells you what A has to be. Likewise, if you solve for C, because there is a pivot in the C column, you get C equals what?
Negative d.
Yeah, C has to be negative D. And then the last equation, E has to be 0. So when we say that B and D are free variables in the sense that they don't have pivots in their columns, we're saying B and D could be anything. Let's just say B equals B, D equals D. You can choose any values you want for B and D, but that fixes the values of A and C and E in place. Whatever you choose for B and D, A has to be -2B minus D, C has to be negative D, and E has to be 0. So you can use this to generate as many solutions as you want. You could choose any numbers you want for B and D and then calculate what A and C have to be in response to that. You can also write the solution much more conveniently in the form of a vector. If you write this as A, B, C, D, E as a vector, we know we can replace A with -2B minus D. B, we're just going to leave as it is. C, we know we can replace with negative D. D, we're just going to leave as it is. And E has to be 0. So now we've taken our vector of 5 unknown variables and rewritten it in terms of just 2 unknown variables. And we can then split that up based on the variables. If we have a vector of just the B parts and a vector of just the D parts, like the top value, -2B minus D, I'm going to write that as -2B plus -D. Second part, we've got 1B and no D at all. So I'm going to write 1B and 0D. Third component, -D, that's no B and -1D. Fourth component is just D, so that's no B at all and just 1D. And then the final component is 0, so no B at all and no D at all. So we're just taking this vector with 2 unknowns and splitting it up into 2 vectors. The advantage of that is that now this first vector has B in every term. So what can we do with that B? If the same variable shows up as a multiplier in every single part,
Multiply by 1/b.
Sort of, yeah. We can't really multiply the whole thing by 1/b, but we can factor out B. So we're multiplying each term in it by 1/b and pulling out the B. So we could write this vector as -2, 1, 0, 0, 0 times B. And likewise, we could factor D out of this one. Every component of this vector has a times D. So we can factor out D and get -1, 0, -1, 1, 0 times D. What that tells us is every solution of the original system of equations can be written as a linear combination of these 2 vectors. Something times -2, 1, 0, 0, 0 plus something times -1, 0, -1, 1, 0. In fact, what would be the easiest numbers to use for B and D? If you could fill in any value you want for B and any value you want for D, what would be the easiest numbers to use?
One.
Yeah, maybe we just plug in 1, or even just 1 for one of them and 0 for the other. Like, let's say we let B equal 1 and D equal 0. Then this term drops out and we just have -2, 1, 0, 0, 0. So one of the solutions to the original system of equations is A equals -2, B equals 1, and the rest are 0. Or if we set b equal to 0 and d equal to 1, we just have, this drops out and we just have -1, 0, -1, 1, 0. So another solution is for a to be -1, c to be -1, d to be 1, and b and e to be 0. But we at least know that e always has to be 0. And we have any combination of these will work as a solution. So you could create infinitely many solutions by choosing any number you want for b, any number you want for d, and adding these together. But the simplest solutions to use would just be just this one and just this one. And of course, b and d could both be 0, then you just get 0, 0, 0, 0, 0 as a solution, which will make all these equations true. But that's typically called the trivial solution because it doesn't really provide any useful information. We want to know what are the non-trivial solutions. We just found 2 simple non-trivial solutions and the fact that linear combinations of them will build infinitely many more solutions. Any other questions on that?
So what would you write as your answer?
I think I would write A, B, C, D, E as a vector equals this linear combination. And then you might say where B and D could be any real numbers. Or alternatively, you could also write that as span of these 2 vectors. Span just meaning the list of all possible linear combinations of them. So there's infinitely many solutions, but we know they can all be written in this format. And this general process can be used for solving any system of linear equations. Write it as an augmented matrix, row reduce all the way to reduced row echelon form, RREF. Rewrite any remaining non-zero rows as equations, isolate the pivot variables, in this case, A, C, and E, and then write the solution as a vector, or more ideally as a linear combination of vectors. This general process is called Gauss-Jordan elimination, if you want to look up more information on that. So give that a try. Try out some more examples. One of the nice things about this is that you can use this on any system of linear equations. So if you've got old notes from previous math classes where you're dealing with systems of equations, whether it's 2 equations, 2 unknowns, or anything larger, you can use this same procedure on any system of linear equations. Give that a try, see how it works, and I will see you next time.